Yo, in this video I'm going to play the Crackmesone CTF that just started today, actually tonight, last night, 12 UTC midnight. So I've literally just registered, I've not opened any challenge, so I thought I could share my entire thought process with you, but sometimes I might be a bit silent because I might be thinking, and while thinking, at the time of thinking, it's not easy to share your thought process. I can share afterwards though. So I thought to stay invisible in the scoreboard. Actually, let me see if I can stay invisible. No, I can't. Is it possible? Scoreboard is empty. Who are all of these people? I don't know anymore. Anyway, so let's get started. I'm not going to submit any flags, and of course you are going to see this video once the CTF is over. So yeah, the flag for the first one is that. Let's get started with CryptPad. Let's take a look at the solutions as well. We see that people played sequentially, so let's get started. Okay, we need to create a folder as well. So let's go. CryptPad it is. In the rules they state that it's a reversing only CTF, so there's not gonna be any crypto or any other category mix. It's pure reverse engineering. I kinda don't like that. I like combining multiple categories like crypto and reversing, but let's take a look. Of course, we're fine with that. So the first one is an exe, of course. Fuck my life with this notepad shit. Okay. Okay. So let's get started. Let's open the folder again. Sorry. Okay. So this is the binary. Let's drop it into an analyzer like that. Phasm. So it's pure assembly. Okay. And the flag is encrypted. Like what? Okay, the flag is 64 bytes long. This is an indication that it might be encrypted with some block cipher. Yeah, because 64 is a multiple of 16, and most probably AES. So yeah, let's also take a look into pbear. All of this is pre-work before opening IDA. We don't want to open IDA immediately, as some initial analysis is always cool. So yeah, there are some okay, I can see a message box, send message. Okay, so I think there is UI. Oh, system function 036. I remember this one. This is RC4. If I'm right, is it? Oh no, it's RTL gen random. I think RC4 is 34. Is it? Is it Cryptographic, of course, it's cryptographic. Cryptographic. 032, yeah, 32 is RC4. Anyway, okay. Create file. Okay, let's open it up. I don't know what is Phasm compiler. Assembler. Okay, cool. So let's open this up. Inside the. Okay. Oh, it has a UI normally. I suppose we can open this up, but not now. Wait a minute. So load menu, nothing. Message. Okay. Text. Startup failed. What the fuck is this? Call. Some error messages apparently. This is some UUID. Yeah, probably. Okay, let's see the strings. CryptPad is an encrypted notepad that uses a custom encryption algorithm to keep nodes safe and secure. To register, send. Okay, I'm gonna do it, of course. Okay, I can see this file appears to be corrupt. Okay, I can see a decrypt string. Oh, it's a string. Yeah, it has no references. So I press Alt A and convert this to a Unicode C style. Same with this. Of course, these strings apparently have no references. Yeah. So, yeah, no reference, of course. So, okay. Okay, this string has also no references. Okay, what about this? No references. Okay, cool. So, get dialog item text. What is this function? I don't remember by heart. Retrieves the title with a control, the title or text associated with the control in the box. Okay. There sends a WM get text. Okay. What is this? It's an empty. Oh, this looks like a key. How long is it? 3, 4, 5, 6. No, it's not a key. What about is this? Okay. So what's the third argument? The buffer to receive the title or text. Okay. A handle the dialog box. The identifier of the control whose title or text is to be retrieved. The handle. The identifier, sorry. So it's okay. Are there any names about this? Okay, is there any any example? No, I won't get dialog. Yeah, ID. So let's search ID. Okay. Okay, nothing interesting. Yeah, no. Okay. Okay, apparently nothing interesting with that. Let's go ahead, move to the start. So this is the title probably. What is this? Yeah, this looks like the main function. We're going to take a look in a while. Load icon. Apparently this is an icon. Okay. From the this is embedded somewhere inside the binary, I guess. Maybe not. Anyway, I don't know how it works. I don't care very much. So, yeah, this. Okay. So I think nothing else interesting. Yeah, let's take a look at. No, this is. There's also this. What is this? PopEx, JumpEx. Okay. Okay, let's drop it for now. It doesn't look interesting. So let's start with this method. Okay, send message. So this returns nothing. Okay. Set window text caption. We've not even run this binary. I don't know how it looks like. Anyway, so send message A. Apparently, additional message specific information. Okay. So, use a customer. Okay. That's for P. O is for registering. F does something else. G does something else. What does G do? I can see the flags. Oh, encrypted files. String. Okay. Get save file name. TXT. It's a TXT file. So what is this? This receives one argument and each of this type. Okay. So a pointer to an open file name structure that contains information used to initialize the dialog box. Okay. Are there any enums for this? Of course not. Okay. What does the structure look like? So I think it's better. Okay. I think it's better if we define it as a car star. Yeah. Fuck this. No. D. No. Okay, let's go. Let's move on with that. No, I want to convert to data. Yeah, and then define array of length for C. Okay, what is for C in hex? 76. Okay. Ah, okay. This looks legit, but this is +4, man. So is this a 32-bit binary? Oh, it's 32-bit. Okay, so it's +4. So it's not 76, but it's 76 D words. So that would be 3304. So yeah, let's go here, and we need to create a D word and then define 76 of them. Let's see how it works. This doesn't work like that. No. What? IDA's kill issue. Yeah. Okay, let's define. Okay. First of all, let's create a struct. Let's define the struct. Okay. So let's undo this. Let's keep it like that. Okay. And let's manually go ahead and define these values. Wait, actually, wait, what? Oh, we already had the lol. We already had the attributes here. I don't know why I had to do all of this. Anyway, okay. str file. So this is empty. str filter encrypt files. Okay. So this defines some kind of struct. If result. Oh, so I understand. This sets up apparently. Yeah, this is a save file. So you get presented with a save dialog, and it asks you where you want to save the file. Yeah, and these are the filters. Only encrypted files, and it asks you to save this file. Okay. So interesting. Send message. What is this? Okay. What is this? Comic Sans. Oh, this is a font. Okay. If v5 create window xa. What is this? Enum. No value. What is this? Nothing. Is this constant something standardized? Deploy application. I'm not really sure what this is. Okay, can have it. I don't understand what this constant is. MATLAB? What? Get the fuck out. Generate go define the references and match the necessary bits. Anyway. And what's his return value? Is there a num for this? No. Okay. Interesting. Okay. I guess. Oh, this looks interesting as well. So I think this is where the encryption happens. And apparently this function is garbage. Yeah. This option is only available in the full version. So I guess this is decryption. And this is encrypt, apparently. No, sorry, not this. This one. Yeah, all other functions are garbage. So let's take a look at this. Okay, so it receives no argument. Ah, yeah, it takes the text. Yeah, it takes the text length, and here it reads the actual message, the actual string to be encrypted. Okay, so number of bytes written. So get window text length. Apparently this is get window text A. Apparently this is a H window, so let's rename it. Okay, let's define it like that. The random buffer length is encrypt option. Let's rename it like that. So it looks like the encrypted flag is written in this with this method call write file. So apparently this method encrypts the data. Okay, so number of bytes written. Okay, this is some 34, 5, 6, 7, 8 byte thing. Oh, okay. Does this... Okay, so we have the seed. This is the seed. Let's take a look at the... how it's called? Chrome OS? No. Chrome OS? No. No Chrome OS. Chrome... Oh. It's general. Okay. RTL gen random. Okay, so what's that? 0? Ah, no, it's not 0. Okay. So what does write file receive exactly? This receives a pointer to the buffer containing data to be written. Okay, so this is the buffer raw data, something like that. And what's the third argument? Number of bytes to write. So this is number, oh sorry, so this is number of bytes to write. Okay, number of bytes written. So what does this function do? Okay, this looks like AES. We're going to take a look at this. So encrypt. This is interesting. This takes, but we don't know how long is the flag, right? Let's rename this for now and run it. Apparently this doesn't work. If we click new, nothing. If we click encrypt and for example take this, so we re-encrypted it, lol, and it's 4 byte for 64 bytes again. Interesting. This is weird actually. This is 0100. This is 1C. Oh, this is the length. What is this? Let's take a look. I don't see something interesting. Okay. Okay, so raw data. Apparently, yeah, this displays the file to be created. This is the file handler. So it opens the file. This is the file. No, sorry, file name. This is the file name. So get window text. It reads the window text that many bytes, number of bytes written. Okay, makes sense. So it reads that many bytes from the window text. And apparently it appends the random bytes. So RTL, let's look at RTL gen random. So a pointer to a buffer that receives the random number as binary data, the length in bytes of the random buffer. So this is how it works. This function generates some random bytes and appends them to the raw data being written, being read. And then 8 random bytes are generated, which are written here. What was that? A notification from the CTF? Rate limiting. Yeah. Random buffer then 2. Okay. Gen random data. Okay, this is interesting because it looks like the actual random data are appended to the data being read. So encrypt raw data, number of bytes written, and now it goes ahead and to encrypt this data. So this is plain text. This is plain text length, and this is a flag. I don't know what this is. Okay, so okay, it copies that. Okay, create. Does some how is this initialized actually? Is this is initialized dynamically? It really looks like a block cipher to me, even though there is okay, this is the key. What is this? This is pretty large. Anyway, so this returns the number of bytes to be written. So apparently we want to see where is the plaintext written at all. How is the plaintext written? Yeah. This is V7, so this is XOR. Okay. So yeah, V7, this is just like that. Then what about that? Okay, V20. V20 is the plaintext. V32, V20. Okay, this is a big guess function. Of course, I don't think it's intended to understand how it works. I think actually I can see only XOR. So what if we run the program and override the random bytes written from the gen random? We override them to the new buffer. So what I mean, since this actually looks XOR, pure XOR to me. You can see that this is the table being initialized dynamically on the runtime, and the final result is just XORed with the plain text. So this looks like a string cipher to me, not a block cipher. I was wrong. So yeah, I'm thinking that if we override the random buffer, then we can probably replicate the entire thing, and since it's a stream cipher, encryption is decryption. So if we pass it the ciphertext and we manage to generate the same keystream, then ciphertext XOR the keystream will produce the plaintext. So let's take a look at how this can work. First, we need to understand how many bytes are appended. So let's go ahead and write, let's remove this. So let's make a dummy flag, like flag for testing. So let's create something like this. And then run it through a debugger to understand how it works. Where is it? Okay, so let's put a breakpoint at what method? Let's put a breakpoint at basically this, yeah, this at this call, at this address. So let's put a breakpoint here and let it run. So file encrypt. Okay, the breakpoint was hit. Now on files, flag.txt. Now we want to override it with flag.txt.enc. Okay, and this is the RTL gen random thing. So apparently this buffer stores the empty buffer. Okay, where is it? Okay, so the second argument should be the raw data. It's not. The fuck happened? I'm not. Wait, give me a second. So yeah, I'm missing something here. Yeah, I'm definitely missing something here. Give me a moment. So let's run it again, and now let's pass it. Why the breakpoints here? I don't want to breakpoint. Okay, all files flag.txt. Yes, let's override it. Oh, it was overwritten. Oh no, breakpoint hit. Okay, so again, where is the okay, let's put a breakpoint at get window text. Let's run it again. Let's put a breakpoint here and encrypt. All files, FLRSCRNSVR.SCR. Okay, get window text. Apparently, is that the one? Where is my fucking input? I know I'm missing something dumb here, I'm pretty sure. So this is just a single byte. Anyway, let's generate the... Okay, this is system function 36. So we generated 64 random bytes. Okay. And then push edx. This should be now 8 random bytes. Okay. So where is the so EAX is just 1. What is EAX? What? Number of bytes? Wait a minute. Wait a minute. Where is the buffer? So it's null. What? So my input is null. So this is a 64-byte buffer, and this is my plaintext concatenated with a 64-byte buffer. Is it? Yeah. Okay. Anyway, let's skip this. And this is the encrypted null byte. Okay. And let's write the data and close the handle and see what we get. We can see that we get the encrypted plaintext and where is the random buffer? Wait, this is not the entire thing. So it's 64. So how much is written? For fuck's sake. Oh, this is the 8-byte buffer. Okay. Apparently, let's make a copy of this and remove that and let it run again. Okay, let's run encrypt this time and pass it the encrypted file. Yeah. think it accepts only, no, I think it accepts only enc files. No? So this is EAX. This is the random buffer. Let's open the copy. Okay. Oh, whoa, whoa, whoa. Push EDX. No, sorry, EDX. So this would be the 8-byte buffer. What about that? Anyway, okay. I think this is the encrypt function, so let's rename it. No, it's how is it? Label. Yeah, it is encrypt. Okay. So this function receives the EAX, which is 1. This is the plain text size. So let's go ahead and, yeah, apparently this is it. Does not make any sense, right? So 73 5B, 73 AB. 5B, 73 AB. This is the random buffer, right? And let's take a look at the encryption. This is it, and when it runs, apparently this is the plain text size, so the flag is 28 bytes long. But why it's empty? Does not, I don't get this. Anyway, and it wrote some stuff here, which should be 8 bytes. Yeah, this would be the 8-byte buffer that we generated earlier. Anyway, I think there's no workaround on this. Yeah. I assume we'll have to go through it. Okay. Okay. So let's run it again. Let's remove this, rename it back to flag.enc. Okay, and let's make a copy and really understand why it does not work. Get window text. What the fuck is wrong with you? Okay, get window text length. I think it looks at something else. Oh, it's a notepad. Wait. LMAO. Oh my god, it's a notepad. Oh my god. Dude. Come on. Let's make an 8 byte, a 28 byte long buffer. 3, 4, 5, 6, 7, no, 3. Wait, let me count this. This is 29, this is 28. Okay. So let's make a fake flag and encrypt it. Okay. And save it here. Oh, now we're talking. Now we're talking. I am completely stupid. This is a notepad. The messages were, the strings were clear. This is a fucking notepad. So we need to write something. Okay. So yeah. So let's look at. This is our input. So a null byte is written, and then there is a how long? This is 64 minus 28, 36. Is it 36? So 32, 33, 34, 36. Is it? Is it though? I guess. Anyway, okay. So, oh, telephone, wait a minute. Okay, so this is where the random buffer is written. Int buffer. Okay. Okay. And encrypt is called, of course, with our pointer, the pointer to our input. So yeah, this is the entire buffer, and it's how long? For 1C. Where is it? Wait, this is 3. This is the random buffer. Yeah, this is the random buffer. So this is the entire 64 byte thing. Okay. And we okay, I already have a solution plan. And if we encrypt it, we get garbage. So this is the now 1D is written. This is apparently the flag length. So we have to make a 27 byte flag, not a 28 byte flag. But most importantly, we need to override. So the solution to this, there are two solutions for this challenge. We can either go ahead and implement the decryption thing, or re-implement the encryption algorithm and figure out the decryption algorithm, or since it's a stream cipher, we can let it run until the first call to RTL gen random. So let's run it again. I will show you what I mean. So this is a 27-byte flag, okay, and we encrypt it to something like flag dummy.enc. Okay, of course, let's run it. Yeah, so now that we have the pointer to our input, this is the pointer to our input, so now the random buffer will be written here, I think. So let's run it. Yeah, I think this should be included as well. It's 30, no wait, it's 64 minus 27, so that's 37. I'm not really sure. Wait, the random buffer length, it's 64 minus, oh, okay. Okay, so it should be 37 bytes. Anyway, we don't care. But the important thing is that we can open the flag.enc and skip the first 28 bytes. So this is 30. This is I think we need to skip these bytes. Wait, this is 16, right? 17, 18. Yeah, we need to skip these bytes and write this buffer. Doesn't look right to me. Wait, the encrypted buffer is actually written over. It's encrypted. No, we cannot do this. The encrypted buffer, the random buffer is encrypted. Oh shit. Wait. This is okay. Anyway, let's go ahead and run it. At least let's overwrite this buffer if it's possible. Okay. So this is where the encrypted data are written. This is 1C. You see we get 1C again. It's perfect. And now this is the random buffer. So this is 4, 5, 6, 7, 8 bytes. Yeah. So what if we overwrite the last 8 bytes? So this is 8. So the 8 bytes generated with the actual flag are these bytes. 4, 5, 6, 7, 8. These are the 8 bytes that were generated. So let's remove this file and run it again with the fake flag, of course. Wait, is anyway, okay. This is the fake flag. Encrypt. Oh, breakpoint hit. Yeah, we don't want breakpoint. So dummy.enc. Let's say let's say, yeah. So that's 32. I think these bytes were written. Okay. For some reason it's 36, not 37. Anyway. Yeah. So now, so this is the buffer that will be encrypted at the end of the day. This is the buffer, 64 byte buffer. And we can say that this is the key. This 8 buffer is the key. So we can just go ahead and grab these bytes, which is the key of the cipher that was used to encrypt the actual flag, and let's overwrite this. Now that would be, wait, how are we binary? Okay, let me copy and paste. Yeah, okay, we overwrote it. But apart from overwriting the buffer, the key buffer, we also need to overwrite the encrypted the data to be encrypted. So this is what is going to be encrypted right now. We need to overwrite it with the data, with this data. Right? Is this it? No, it's not. We can probably copy the entire thing. Yeah, so let's overwrite it and let it run, and we get the flag. We don't care about the rest bytes. Of course, they are trash. Actually, they are not decrypted at all. Okay, they're not touched at all. Ah, so it reads the plaintext size from this, from here, so we don't have to bother at all. We can put anything we want here, but the first 27 bytes needed to be strictly the encrypted flag. So yeah, we get a flag like that, which is actually, let's write it to the file. Yeah, let it run and we'll get the flag. Roll your own bad code. Yeah, this took quite a while actually. I'm not rushing or anything. There's no need to rush. I take my time, understand how it works. Yeah, this is pretty much it. We could go ahead, of course, and statically analyze the cipher and re-implement it entirely, but I'm kind of bored right now. I mean, all that matters is this 8 byte buffer, which is the random key buffer. Is this actually just XOR? What? Are you serious right now? Give me a moment. Oh. Bytes heap C for heap C in zip AB. Okay, so this is XOR method. Let's grab the encrypted flag. This should be 28, 27. Let's grab this. So this is enc flag, bytes from hex. Key, the key is the last 8 bytes, so this. So let's try. No, of course it's not just XOR. Actually, I'm kind of curious right now. Wait, let's go ahead and run it again. Okay. Encrypt. I don't want to breakpoint here. Stop it. Okay. We don't care about all of this. Let's go here and put a hardware breakpoint at actually at access, yeah, and run it. So the byte is loaded at this line, so let's press Alt Insert to copy the address and jump here. Where is the address? What? What? I don't understand, this is very buggy. Anyway, okay, this XORs apparently this is the 8-byte buffer, yeah. EDI, yeah, so it XORs, okay, so it's just a simple XOR. It's Control E, yeah. Let's yeah. Where is the ESI? Okay. So no, wrong. Let's Control B. No, Control Shift B. No, Alt Insert. No. Okay, so it is just flag. No bytes. It's XOR flag key. Yeah, this is just XOR, and it overrides. Yeah. Apparently, this shit just XORs. So this just XORs the 8 bytes. There's some more thing going on here. I don't know why it skipped. Oh my god, let's run it again. Oh my god. Anyway, let's use the actual flag. Yeah, fuck off. Yeah, remove the breakpoint. Yeah, we want out.enc. Where is it? Why is this so buggy, man? Why? Why is this so buggy? Crypt. Why is it break pointing there? Why? Don't get it. Out, don't hang. Okay, thank God. Let's put a breakpoint. So okay. So let's move on to that. So let's see which bytes are written. Now what? 8 bytes. Ah no. Oh yeah. Now what? Huh? So what? It just repeats the random buffer. So it just repeats it. So for example, if we say that this is the flag and the key is bytes from hex. Suppose that this is the key. XOR flag key and key. It does not look right at all. I think I copy pasted something wrong. EDI. Wait. Oh fuck, EDI is increased. Oh. Wait, EDI is at D0. So that would be it. So is the 8 buffer. Wait, random key buffer. Let's go to this address 24C5. 24 6, yeah, this is it. So this is the buffer 3, 4, 5, 6, 7, 8. Yeah, let's go paste this. What the fuck is going on? Yeah. But you remember that these bytes were different initially, so yeah, it's not just XOR apparently. Yeah, it is not just XOR. So there are some alternative solutions to this. We could also emulate this function with Unicorn or something like that. Let's close all of these two main files. So yeah, let's have flag.txt in a file. Okay, flag.txt locked. So the other approach would be to store to run this encrypt function in an emulator. Since it does not have any API calls, we can just run it in Unicorn and manually set the plaintext buffer as the encrypted flag. So, and set also the random buffer to these 8 bytes that we want, the key buffer. So set the key buffer accordingly based on these 8 bytes and set the plaintext to this, just like as we did in the debugger, but we can do it with an emulator and let this function run, and then if we print the encrypted data, which are the decrypted data basically, we get the plaintext again. And the other approach is just to statically analyze the function, the entire function, and re-implement the algorithm statically. We could do it as well, but it would take a lot of time, and I think the purpose of this video is just to showcase the CTF and not how to re-implement algorithms statically. This would be a topic for another video. So let's go ahead with the next method function, with the next challenge. I am already burned out. So what is this? Flare screensaver. Flare? What is this? Oh, Morridge is oh. I think he's a oh, my videos. I think that Morridge is an author of this year's FLRSCRN challenge 7. Morridge, yeah. Oh god, let's go. What was the 7th one? Oh yeah, the C2. Yeah, so let's go. Download, not download. This should be fine. This is a flare and this is a SCR file. I am already bored with this. Edit. So this is basically binary, we can see. Okay, let's open it up in here. This is a C++ file. pbear, I think it will throw an error because there's no extension. Oh no, perfect. Debug. Do we have symbols as well? Flare, wow, a Crackmesone screensaver, I love it, thank you, ho ho ho, PDB. So PDB. So section headers. The resource header is huge, so it might be interesting to inspect it. So what about the imports? A lot of dummy imports. What about the resources? Okay, so let's open the resources bitmap. This is a frog. Apparently all of these are just, yeah, okay. Okay. What is SCR file screensaver? Watch out for SCR files. Is a Windows screensaver file which acts as an executable designed to display animations, graphics, or slides when the computer is idle. While intended for screen protection and energy saving, these files are essentially executable, making them capable of running malicious code. Yeah. How to open SCR file. Okay. SCR, yeah. Okay, let's go ahead and directly analyze it. And as always, remove the extension because I might accidentally click it. So yeah, it is an exe file. I don't want to connect to Microsoft Symbol server. And let's go ahead. I think this is some boilerplate code, no need to analyze it, right? Yeah, apparently. So what is interesting? We need to find for interesting stuff that stand out and are not standard. Oh, what the fuck is this? Crackmesone.1. Oh, this sets a register key. Okay. Quack. So it opens this registry key and writes and what does what? Oh, okay. So I think it writes this value to this key if it exists, something like that. Oh, it looks like a ransomware actually. What the fuck is it? It scans for DLL files? Why? Nothing interesting. So let's go to the other files. Keep calm and flare on. Hopefully this is more interesting. This is a huge function. Let's filter the functions based on their length. Okay, Queen main is large, very large. What about this? This is even larger. Okay, I can see a pattern. There are many functions that are scanning for DLL files. Here's some weird random stuff. Okay. This challenge might take a while. Yeah, I can see a lot of patterns. Keep calm and flare on. Yeah. So what? Draw text. So just writes this text. Anything that looks like an encrypted buffer. Anything at all. Like, the encrypted flag should be somewhere, right? Please don't tell me it's inside one of these images, like the frog. So let's take a look at this weird string that looks like a permuted alphabet, or this one. They both reference the same function, that's good. So this is weird. Okay. So it concatenates this. Oh, there's some XOR here. That's interesting. Oh, this is RC4. Oh, oh, this is just obfuscation. I see. Oh shit. This is just pure obfuscation. What matters is these lines. Okay, this is interesting. All these DLL calls are just garbage. If you notice, it just scans for a directory, concatenates, finds the file, and just close the handler. Does nothing else with that. Literally nothing else. So this is just obfuscation. I see. What's this? Oh, this is flare, the string flare. Okay. So take a look at this. Yeah, interesting, very interesting. Okay, this is RC4. And how did I see that? Because of this line. This is a standard line that we're talking about, RC4. Take a look at this. Wait, for example, this. So it's J mod something plus J, and the reference is something. So look at this. And then this is the byte. Wait, this is the length. This should be the length of the plaintext, and this is where the actual plaintext is taking. So row buffer, let's call it row buffer, and it looks like pointer to 16 bits. If you look at the assembly, where is it? Yeah, I think it's a UTF-16 string. So each byte is representing as 2 bytes basically. It's a null byte and the actual byte. Yeah, so this is the key string. This is the J, the counter. Okay. ST. And let's see. What is V32? V32. V32. Okay, let's take a look at this function. We said that all of this is obfuscation, right? So there should be some important stuff going on. Honestly, what does this do? Yeah. Honestly, any other function looks pretty trash, useless. This is where the fun begins. This is where the fun begins. What about this? This is also garbage? Yeah. We don't care about it, we just want the flag. At this point, this is just obfuscation. We could run it, but if we run it, it's like debugging a screensaver executable, and I think this is gonna be painful. Okay, this apparently looks like some encrypted buffer or this. Some of these strings might be the key, the RC4 key. So let's start by this. Okay, so v10 is the key size. No, what's that? So it's plus j. Yeah, this is definitely the initialization routine. No, it's not. What? 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 It's what the fuck is this? J is the counter. Okay. This okay. V11 should be the length of the plain text. Yeah. So row buffer length. See that? So this is the row buffer length, and this loop runs. Okay. V43. What's the fuck is this? Okay. This is V17. Destination. What is destination? Oh. Oh, this is the entire alphabet. Okay. A B C D F G H I J K L M N O P Q R S T U V. Okay, this is the alphabet, no permutation. This is just the alphabet. Okay, so this is the ASCII alphabet, let's say. And this is permuted encoded alphabet, let's say. Oh, it's a reverse thing. Oh, okay. Reversed alphabet. If you can see that, it's literally the reverse thing. Okay. Yeah, it's a reverse alphabet. So, does some stuff. V32. What is V32? Okay, let's take a look at this. V32 is just a FLR string. FLRSCR. So yeah, let's mark it as no, this is how can we let me see. How no, it's not the word, it's 1 2 3 4 5 6 7 8 9. You can see that these are consecutive strings anyway, consecutive characters. So the string is FLR slide. Okay. Anyway, let's call it FLRSCR. Oh, sorry. What is this value? Anyway, okay, this is the FLRSCR. You can see, for example, that this is the literal obfuscation. It just calls get tick count, and then just sets the last error to that. This is purely garbage. Or this code just does nothing important. Okay, so this is it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So this should be 18. Why? Yeah, it doesn't work. I think this is right. 60 words. 1, 2, 3, 4, 5. No, this is 5 actually. Yeah, I'm not sure. Let's keep it as is 6. Maybe it's a null byte as well. Yeah. Okay, so the raw buffer is short with this. So this is the FLRSCR length. Okay. Plus J. Can we do it like that? No. Can we make it a pointer to the word? No. I want to make it look like an array. But anyway, this is equivalent to J plus FLRSCR J mod length of FLRSCR. Okay. Which is exactly what this looks like. Okay, maybe it's not really RC4, but it really looks like it. Anyway, so raw buffer, what about it? V12, what's V12? Should be 28. Okay. So V25. Yeah, this is literally garbage. We could just knob everything out, but it would take a lot of time, so we don't have to. So what is going on? So what does this function do? Let's take a look. I can see where it goes, but I still have some things to figure out. White color multi-byte versions, strchr. Yeah, okay, I know it's okay. These 2-byte padded strings that we said that these bytes use two bytes actually to store each byte, so a null byte and the actual plaintext byte. This is called a wide string. We have already talked about it in another video. So strchr returns the first occurrence. Okay. So how okay. So raw buffer is written from the reversed alphabet. This is the reversed alphabet. But what offset? So it looks for, this is a pointer. Wait. First of a curve from given this parameter given a string. This parameter refers to be searched. Okay, so it looks to the already existing raw buffer, okay, which is the input, okay. So it takes the offset of each character in the raw buffer in the ASCII alphabet. And so it's like a permutation cipher with along with XOR. Yeah, it looks, for example, suppose the raw buffer is Aris. So it looks for A inside the ASCII alphabet, so this returns 26. Then R, it returns this corresponding offset, and so on and so forth. So the cipher is pretty simple. That's good. But the offset is very weird, actually. What? It subtracts the point. It's okay. It's the offset. Yeah, it's the offset inside the alphabet. Yeah, it's literally a permutation cipher. So let's see how it's called. How this is called. This is initialized from here, and this is the raw buffer. Lol. So this is the raw buffer. This is the source. Okay, let's move the opposite way. Okay, this is where the fun begins. Yeah. So the source length. If source length is 25, what's that? I mean, this loop is literally useless, man. This has the value of 5 and just runs 5 times. And then v13 is not used at all. This really looks garbage. Yeah, this is garbage. So we know that the plaintext is 25 bytes, right? So what's the source? What's the source? What's the source? What's that? Yeah. This is the flare screen save. So let's write some things down. Alphabet. This is the alphabet. No. Along with this. Rev alf. It's reverse one. Okay. So I don't get it. Where is the plain text? So row buffer is initialized here, and source. Okay, the buffer is 256 bytes long. What? So what if the source length is not 25 bytes? Nothing. Okay, so we know the flag is 25 bytes. Okay. What about source though? Okay. So okay. We need to find the source basically. But this is garbage, right? Yeah. Okay. Is this the encrypted string? Wait, is this it? So what would be 60 plus 50? 6502. Oh fuck yeah, this is the encrypted thing. Is this it? Yeah, I think this is the encrypted thing. And flag. So where is it used? It says this value 52. Yeah, makes sense. And okay, it copies that. Destination, and there's nothing. Okay, I see. Let's make a Python script for that. Okay, so we have we can literally reverse this. Solver.py. Yeah, it's literally the reverse thing, right? Yeah. Okay. So the final encryption. Okay. Okay. So the final encryption. So is this really it? Is this... Do we actually need the row buffer? What about... okay, what's the row buffer? Alright, so... so it loads this encrypted thing. It actually loads the flag, okay? It shows you how is the flag encrypted. I see. Okay. So this is expected to receive the flag here, not the encrypted thing. So this is how the flag was encrypted, and so this is the encrypted flag. Okay. So let's go ahead and, you know what, actually we can make an array of 52. Yep. No, it's longer. The fuck. So it's 58. Hmm. Okay, yeah, this is not what we want. This is not what we want. This is just, so this should be, sorry, it's 26. Yeah, it's the words. It's just words, not color. Yeah, this is an array of words, not bytes. So it's 26 divided by 2. Okay, so let's grab the encrypted thing. And I think we need to replace bytes from hex. So this is it, and we want to eliminate this. Is the encrypted flag. This should be 52 bytes, hex characters. So the encrypted flag is this. Okay, I think the null byte is wrong. So this is 50 exactly. Perfect. The key, if we can say, is flare. Wait, not flare. It's key is flare. Ralph. Maybe this is not true. Also, don't know. So le a r a l. Okay. Yeah, this is Valve. Okay. So first we need to XOR this thing, and then we have to reverse the permutation. Okay. So for I in range length of the encrypted flag, so we have to, let's make it a list, so a list of integers significantly. So we have to enc flag let's use enumerate. So this is E short with this thing is key. Let's make it key. So this is E XOR key. This is J plus. No, wait. No. J plus I. Sorry. I key I. Mod length of key. Is this it? Wait, I fucked something up? No. This doesn't look like right at all. Nice. I think this is a problem now. Uh-huh. Uh-huh. I assume that we have to get these characters in the end. I'm pretty sure that the characters we get at the end should be included only in this set of characters. Otherwise, we have invalid decryption. Yeah, of course we have invalid decryption, and we need to figure out why. I think I know why. It's this addition thing. Yeah, this is okay. This addition is done and FF. Wait, I mean this. No, it's the same. Then I don't know what's wrong. But this doesn't look right. Should we really work with... Oh my god. Should we really work with words because I have skill issue? Okay, I might get some help from the LLM here, just to save some time from your lives. Can I just debug this? No, I think it's gonna be annoying. I don't want to put a flare screensaver in my PC. So yeah, okay, work PTR, adds IX and source. So wait. Hmm. I don't see that. What? How is the same thing? I literally just changed the key and the result stayed the same? What? Yeah, actually we don't need... What? Wait. What the fuck? CHR. Flare, 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 flare. What if we add alpha? Flare, alpha, flare, alpha, flare, alpha, flare. Okay, so the sixth character should change. 1, 2, 3, 4, 5, 6. It changed, yeah. Okay, okay. Mm. I'm having skill issue. I hate this kind of ah. 6516809020725033008. It's correct. Okay, let's work with words instead. Okay, so the key. Okay, you know what? Let's reverse this. So let's make it. Laugh. Of course not. It should be flare, yeah. So let's make it. So it's F null byte L null. Oh, no null byte after L. Ooh, ooh, this is scary. A null, R no null, E null, R A null, L enter. Okay, and let's copy the encrypted flag as is. So 0B, so this should be 100 hex, so 50 bytes. Yeah, makes sense. And now no, this is wrong. We need no right in range 0 length of encrypted flag per 2. So E is flag I plus 2, and this is int from bytes in little endian. So this is the byte, and okay, this looks right, and it's wrong. This is wrong. Is it? Wait, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13 bytes. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's one key. Is this right? And this really doesn't look right. Should be little endian. Since we work with little endian. Yeah, this is essentially. Let's try adding a null byte here. Okay. Doesn't look right. Okay. I'm really thinking of using ChatGPT right now. Of course, I could just use emulator and emulate the thing, but this is not fun to do because there are these API calls. I really don't understand how the data is stored. So it's f null byte. What's that? Anyway, okay. A null byte. Yeah, but is there actually a null? Ah, it's stored in offsets of 4. So yeah, there is a null byte. Of course there is. So yeah, this is big. No, this is little. Never mind. Okay. No. I think this kinda looks right. Like you see these null bytes everywhere. I like the fact that everything is a single byte. If I remove this null byte here, I get the large values. Putting a null byte here, basically, is there any way to, let me check something. I don't remember by heart. Like key encode UTF-16. No. Python encode wide string. Should this be a Unicode string? I think this will throw an error. Of course. Yeah, this is basically it, but we need to skip the first 2 bytes. Anyway, let's keep it as is. Okay. So yeah, this kinda looks right. I like it that it's just a single byte, but I think that it's what we got before. Yeah, it's exact same string we got before, but now it's much more ugly. I don't get it. What am I missing? So it's I plus the reference of the flare string source. I think oh crap. Yeah, I is incremented by 2 by each time, so we need like that. Yeah. Okay, this kinda looks fine. Like most characters are here, but for example, there are some that are completely out, like the slash. So this is wrong. This is wrong. The parenthesis is wrong. So one. I really don't understand. Should this be an F? Okay, should this be an A? No. Should this be an R? Of course not. Should this be an E? No. Should this be an L? Nope. I think something's wrong with this, with the key. Let's see an orange. Oh shit. This should be No, I think. Wait. The first time we need 0 until 2. Second time we need 2 until 4. Yeah, okay, that's fine. This is correct. Oh, what's wrong? Like, it's wrong from the second character. 1, 2, 3. Fal. Yeah. J plus this thing. Of course, as a word. Yeah, this looks pretty correct to me. Let's ask GPT. I don't want to spend more time on this. So all of these are trash, right? Yeah. So the important thing is that now the encryption routine. My code outputs will be characters to be included in this alphabet, which obviously is not the case now. What's wrong? So I really pretty much copied the assembly, my cipher, and some pseudocode, and just checking what's wrong. I'm really not intending to emulate this right now. I just thought it's an easy challenge. I don't want to try hard. Oh wait, actually we know the flag format, right? So let's verify the first few bytes. Okay, we know the flag format is um, flag format is CMO, right? So assume that the flag runs through this algorithm. So first character is C. So strchr no, yeah, this one. So print alf index of flag format 0. So the okay, it's 28. So this encrypts the character at the offset 28 minus 28 minus the alphabet. Wait, the RDX is what? Okay, so the reversed alphabet. Okay, oh, this is wide strings. Okay, these are wide strings. Okay, so the corresponding character is loaded here, and R15 maybe stores the row buffer. Yeah, so R15 is row buffer. Okay, and it's seriously, so it's assembly what is SAR shift, right? So this shift divide by 1 means divide by 2. So what the fuck is RTX? Okay, so it's 28 minus the pointer. Wait, this is the address? Wait, if that's then they are oh, yeah, it's loading the address of the ASCII. What? It is subtracting the offset in a string. So RDX is an offset, right? It subtracts a pointer. This is weird. This is very weird. But anyway, let's take a look at the character at offset 20. This is M. So I don't understand. Divided by 2. No, that's wrong. Yeah, this is Q, the index is that, and we want to divide by 2. I. This doesn't look right. Okay, so what's the problem? With 2 modulo endpoints, the slice breaks whenever it wraps. Start is equals 16 and 0. And your system is wrong. Oh, I'm not sure. In the SM, the key is accessed in word index. So in pathing should index by J. Ah. What? Ah. Okay, I see. Yeah, or we can make another. Okay, let's do it like that. Sure. Of course, I thought about it, but I wanted to keep it cleaner, I suppose, but maybe this is not possible. So K, yeah, should be keywords, J mod length keywords, right? So it's really this key. It looks correct, and this is correct. Are you fucking kidding me? Okay, let's move to AVM and run this. Oh, this is very annoying. Okay, my PC is definitely going to be very slow now, but I'm prepared. Okay, apparently this is completely wrong. This is ridiculously wrong. Don't see what I'm doing wrong. I really can't understand what I'm doing wrong. Okay. so much lag. This is so sad. Okay. It's copied. Let's move on running it. Let's rename to .scr. No, actually not running it. Let's open the debugger. It's gonna be a tough experience, but okay, no problem. We'll deal with this. Okay. And we don't have stupid shit. So much. Okay. Let's see where is this code. So this is where we should put a breakpoint. So let's copy these bytes and look for them in the debugger. So it's Control B. Okay. Search here. Here you are. So let's put a breakpoint and run this. I don't know what happened. Let's run this again. What? What? Let's check if this function is called at all. Okay, let's play with the registry. So we need current user software. We cannot find the FLR screensaver key set. So once we found that, we need to set a value. Okay, let's do something else. Let's put a breakpoint at this function. Let it run. Okay, let it run, and let's put a breakpoint at this function. What? 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 It didn't even look for this. What? No call to this function? Oh, there's a string behind. Crack. Calm. Ah, keep calm and play. Yeah. Okay. Yeah, it's the string keep calm. Keep calm and flare on. Is this a flare on challenge? Okay. Why doesn't it work? There should be an explanation here. So, okay, starting from main. What happened? Okay. So, okay. Doing, I guess. Okay, let's run this again by adding a /c. Is it /c? /p? Okay, let's run with all the arguments. Lul. And /s, yeah. /c. Okay, it does look like this works. So let's refresh it. The arguments are there. Let's run it. Oh. Oh yeah. CMO test flag. No, actually we need fake flag for testing. Is it 25 bytes? No, this is 26. We need one more less. And this get dialog text A. Get get message W. Get dialog item text. Okay, we put a breakpoint. What about methods? First quick message. Okay, let's run this. Wait, this is our input. How does it know? Is it stored anywhere? What? Okay. Current user. Okay, why? Okay, let's reopen the registry editor. There's somewhere. Oh yeah, this is our input. Oh yeah, and this is the encrypted thing. Okay, so now we can debug. Let's debug this. This is garbage. This is garbage. Okay. All of this is garbage. Where is the no? Yeah, no. Anyway, this function. Okay, we need to break point at 1521. Let's break point here and run this. So this is the alphabet. Of course, it returns oh, it returns the pointer. Yeah, and of course it returns the pointer. And what about it? What? Wait. No, wait. Okay, this is the reverse. No, this is the real alphabet. It subtracts this. I guess, yeah, this is the object. It's 1C. So this is offset 27, so 28, yeah. You can see that the offset is right. As expected. It's M. That's right. Awesome. Okay. Ωραία. Move EX R15. So we need to keep track of R15. Where is the, yeah, this is it. You can see that all of these characters are part of the alphabet. So what's wrong? Moves, okay, it divides by R12. It's 9. 9. Right. What? What the fuck? Oh, oh, it's a length. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So the key is right. It's literally Flare Ralph. Ralph. Flare Ralph. Okay. Let's name it like that. It was correct. So I was correct about that assumption. And it divides. Of course, it's the same. Okay. And it adds this one with F. Of course. And it XORs F with M. And the result is B. Huh? What? Following dump 0B? Okay, 0B. Is this true though? So suppose that, oh wait, oh fuck, this is reversed. Oh my fucking god. Please don't tell me this is reversed. Oh my god. Dude. This is fucking reversed, man. Why? Why? This is not intuitive at all. Why is the encrypted flag reversed? Why? This does not make any sense. Okay. So this is it. And we reverse it. No, actually, it's this thing, but in reverse. And yeah, fuck this null byte thing. We don't need it. We can just we can operate directly at we can actually directly convert the white string to normal string. I really don't understand why the string was reversed. I don't understand. You can see, did you understand why I figured this out? Because you can see that before the C was encrypted to 0B, and now M was encrypted to 0E, which is literally, since we know the flag format, this is literally how the encrypted flag ends. So I thought it's not in reverse, but it is apparently. Anyway, okay. So now it's much simpler. We can length key. No, we don't need this. We can 0ff apparently. I think it's gonna be fine anyway. And this is bytes. That's simple. I am idiot. I am an idiot. An idiot. And Python solver. Oh fuck yeah. This really looks like a correct encoded flag. So once we have this, then we know this is an offset. So what we need to do is that we need to map M we need to find the offset of M. We need to find the offset of M. We need to find the offset of M. No, wait. I'm mindfucked. Okay, we don't need any more debugging. This is over. Okay, so we need to find the so this is M. How was M calculated? By V17. So essentially it's rev alf index of RI. This is basically the formula. So we need to figure out this RI, and the task is to find the offset of M inside that and get the character at this offset. Yeah, so the index of flag I and get the character at this offset. This looks good to me. So this is rev alpha. This should be, what's wrong? Oh yeah. This could be SCHR. Yeah. Fuck yeah. Let's do it like that. No, this is decrypted. Sorry, this is decrypted flag, and this is decoded flag. So no, we need decoded flag to be the result. No, just this, and print the decoded flag. Ah, nice. This looks good. I really don't understand why the flag was reversed, honestly. I don't understand this. It's crazy. Anyway, let's move to the last easy challenge. Let me eat my orange, my vitamin C. Okay. Okay. Nice. Quite easy. If I didn't spend that much time to obvious things, it would take me much less time. But it's okay. Okay, let's shut this down. And no, fuck, it's not, but I hate it. Let's close all of that. It's 3 hours long already. Cool. Yeah, ChatGPT has no idea. Actually, I had my algorithm was correct, but the flag was just not in the correct endianness. Anyway, so something's wrong with this record player. This music doesn't sound quite right. Your mission is to fix it. Don't worry though, this technology... Fat Mike, who is he? Don't worry though, the technology here is pretty simple. Right below the play button you'll find two switches. One controls the direction of the record spins, the other keeps the pitch steady. Chances are both of these switches are broken. Okay. Okay, let's check this out. I think I'm done for today. This already took me quite a lot of time. Let's analyze this. Okay, it's a large binary, 1.2 megabyte. So what's the readme about? Oh, AI generated description, let's go. Can you see the quote? Lul. So this is C++, tested on Windows 10, x86-64 architecture. Let's analyze this in detected easy, nothing interesting. Let's open PBR, RecordPlayer. Where is it? Yeah. So let's see the okay, the resource. Of course, the resources are large. The resources are large. The resources are large. Yeah. So let's open resource hacker. We will take a look. We will take a look later. I can't talk. So we can see find resource. Is debugger present? Okay. Yeah, this is some classic thing to make a UI. So apparently this is not even malicious yet. Looks what? Okay, I'm back with my 10th Crackme. Like the previous one, this challenge was created for the Crackmesone CTF. Something's wrong with the record player. Yeah, okay, we already know that. I see. So user32.dll usually involves some things about the graphic interface, GUI things. Oh, we don't really need user32 or GDI. All of these things are about the GUI rendering, graphical rendering. But this is quite interesting. We see shell execute. Why would an application that plays music call shell commands? Why would it call shell commands? Let's take a look at this. So FX dialog layout, nothing, binary. This really looks like something. Okay, so it's like the word skip. This really looks some random bytes. Okay, sound. Okay, rickroll, cursor, the buttons. That's why the binary is large, because all of these things are embedded inside the application. It's not that the code is large, it's just large because it has all of these wave files, the image files, and so on. So, and let's open this up. We need to take a look at two things first. Shell execute, why it's executed at all, why it's called. It's pretty sus. And also this binary resource, it looked pretty interesting. Let's take a look. The code is pretty standard, not a lot of code. Let's see the strings. Okay, quite fast. We can see the name of the weird resource. If you remember, it was called binary, and also sound. What's this constant? Looks weird. What? Excuse me. Unity. False flag, fake, false positives, I guess. Okay, let's see where sound is used. So sound is used here. This is some cursed. What's that? Data. Okay. Okay. Sorry for that. Mom message. Okay, unable to retrieve the skin. What's that? What skin? Oh, here is it. Here it is. Close the binary resource. X create region. Okay, this. Okay, I think this is not that important after all. Close the resource and create region. What is this? Was it from user 32 or GDI 32? GDI. Yeah, this is some. This has something to do with graphical rendering. I think the UI. Pointer to create a region from a specified region transformation data. Oh, actually, this could be the case. Actually, no, it's not encrypted. No, 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 no. Okay. Oh, this is in. This is nice. What the fuck is this? This is interesting. This is interesting. What is this constant? Actually, you know what? Let's run it through PID as well. Maybe there are some crypto constants inside that we could take a look. It's a common technique that we do in our reverse engineering process. And nothing stands out. Okay. So what is this source thing? Invoke Watson? What is V5? Okay. Okay, so this returns an object. Okay, we are interested in this specifically. We're interested in the offset 320. Okay. Can we? I like this. can we search for these bytes? Maybe we can find all the references of 320. Let's see. So we can search for this pattern. Search sequence of bytes. Yep. Oh, interesting. Let's see if we can find anything interesting. Yeah, this is initialization. Oh, all of these are in the same function. Okay, right. What about this? V20? Okay, this is some ugly shit. Ugly shit. What about that? Yeah, I'm really not sure what's going on here so far. Let's just have it in mind. Struct init SAS numbers. For example, what is this method? Oh, this is hash function. This is a hash function. I think this is FNV and FNV1 hash. Yeah. Oh, is this? Oh, is this an API resolve function? Okay, this is an API resolve function. I like that. FNV1 hash compute FNV1 hash. So is this called anywhere else? No. Okay, I think we found something interesting quite fast. Nice. So these are FNV1 hashes. Let's use a hashdb hunt algorithm. But I'm not sure it's going to work. Oh. Okay, what about it? Okay, you know what? Let's use the hashdb API. How can I use the API? Get. No, we need hunt. Okay, let's send a post request. What's the base URL? Oh, okay. So curl x post is URL. Curl set data post. Yep. Content and the data are this. No. So it's hashes. Okay. Oh shit. This should be this number. Valid request body. What? What's wrong? Should return two things, right? invalid. Okay. Hash. This is the hash URL. This is the URL and request post URL and /hunt JSON equals hashes h JSON. Should this be a list? Oh yeah. So it's okay. So okay. So request get URL plus /hash /mul /h. This is a get request. So what's wrong? Yeah. What's that? ODF OX32 point oddfox 32. What? Is this a collision? This really looks like a collision. Let's use the other algorithm, Lokibot. Okay, reg set key value. Oh, this is good. So this is add API 32.dll. Okay, I see. Let's search for this hash. No algorithms. Algorithm. I think this is a collision, not gonna lie. Oh, bubble loader. Bubble loader 125 and the hash is, what was that? Was that it? That one? This one? Yeah. No algorithm. What's the name of it? Bubble 0125. So this is msdrm.dll. Yeah, this really looks random. But why does it do the API resolving at all then? No algorithm. What about it? Oh, this is common. Let's see what about this. Where is it? Where is the IDA? Okay, so let's add. No, fuck. This is annotator encriptado. What? Malware? Oh, I think Okay, this could make sense. What about the other one? It's roll 7 XOR. No, I think it's all collisions. Anyway, let's keep all of these in mind, but I doubt that something's wrong here. Okay, let's start with main again. Oh, are there LNTLS callbacks? No. Okay, so start. What's this? Nothing. This is the main and win main. Okay, let's begin our analysis. Struct inits as number. So this is the main. Okay. Okay, some interesting shit. This is the get window long PTR. What's this? I think all of these are just distractor functions clearing up stuff, so the juice is here. So v17, what's that? The table? I don't know. There is some weird things going on here. Get dialog item. Interesting. Just looking around, looking at these functions. Get dialog item. Set window text. Yeah, nothing interesting. Set window long PTR. What about this? Nothing interesting. Okay. So what about the other one? No. It's all graphical stuff. Any weird string? PEAD. Okay, nothing interesting here. Yeah, these are the imports. Oh, what? Debug information. Volatile metadata. Oh, I'm not sure. This dispatcher looks pretty interesting though. Load some bitmap shit. So this is interesting. What about v18? This really looks standard behavior. What about v21? It's the result of this, so it's a pointer to a class apparently. And apparently plus 32 means that I will tell you just now, in case if I know, maybe I don't know. So this is plus 0 plus 4 plus 8 plus 12. No, it's 8 bytes, sorry. So it's plus 8 plus 16 plus 24 plus 32. So this one. So about v18, same thing. Thing is this plus 0 or this? I think this one. So it's plus 0, plus 8, plus 20, plus 0, plus 8, plus 16, plus 24, plus 32. Wait, plus 32? Wait, what about okay, so plus 0, plus 8, plus 16, plus 24, plus 52. Okay, it's the same function. Oh, it's the same. Okay. Console as font. Solid brush. Okay. Oh. This is really the important function. Okay, apparently the interesting stuff happens here. So we have some base classes. This is the main dialog, for example. We have some symbols here. We have symbols. Okay, this is we don't care about this. Plus 0. What's that? What's that? Okay. Structure function wrapper, something like that. So we know the name, so we can avoid it because it will waste a bit of time to analyze these methods. This looks interesting. What is that? Get dialog item, skin, nothing. Track mouse event. So do we really need to fix this application or just get the flag? Yeah, I think this. So these are the handlers for the button clicks. Okay. So what does this function do? The replacement value. So change the navigation of the specified window. The function also sets a value at the specified offset in the extra window memory. Apparently this is not that obvious. Yeah. Let's take a look again. Okay, these are all the wrappers, right? What's that? Okay, I will mark the functions that look interesting. Definitely not this one, definitely not this one, and definitely pop-up dialog. Doesn't look very interesting. Shit. Yeah. Okay. So we don't give a fuck about this, but this is interesting. So let's rename it to SAS1 so we can analyze it later. There is some things going on here. Wave out close. I see. Is this interesting? No. Not at all. What about this? Nope. Structure. What about this? What's that? What's that? Nothing. Nothing interesting. I know I could do something different, but I want to analyze it as much as I can. Of course, I could go just and debug it and find out where the hash functions are actually called, or the hash function. But I'm going to do it in a while. Oh, shell execute. Oh, okay, it's false positive. Okay, it's apparently a link to the author's profile. Okay. Pretty much nothing interesting here. This is weird. What about this? So no more functions. Okay. Then how about sorting them by length? What's wrong? This is the larger function. Lol. This is really the largest function. No, it's not. Okay. So this one is pretty sus. This is the one doing the hash resolving. Very sus too. What about this? This is some main shit. Oh, what's that? Is this some anti-debugging check? So if what's that? Nothing. CPU ID. I don't think this is interesting. In modern C++ applications, there are many false positives, many things that might look interesting, but eventually they're just standard boilerplate shit. Okay, it creates an event, very sus too. Oh, here it is. It is called twice actually. So begin thread index. Oh. What? Okay. let's go ahead and do some stuff. Wait, is this Stego? Yeah, it does not play. Of course, let's drop it. Why? Let's grab the address, copy address. Let's rebase the IDA with segments, rebase program. So we want to rebase the entire program so that our addresses are aligned with those of the x64dbg. So let's put a couple breakpoints here. First, let's put a breakpoint here. And then at VerySAS2, I want to see when these functions are called. Let's run this. Of course, it's not standard behavior. Okay, I click the play button and we got inside the VerySAS function. Wait, are there any encrypted resources? Actually, let me check something. Find resource. Find the resource A and W. Binary. No, it's just initialization stuff. Yeah, nothing interesting. So play. Oh, sound is called, but sound is Rickroll. Right? So where is the handler? Yeah, this one must be interesting. Wave out right. Yeah. So I guess it was called from 21df. Yeah, this. So we are at this point. What's v5? Let's see what's the value of v5, which should be the RDX. Empty. What's the value of RC6? Okay, this is a struct. What are these? Wow, this challenge is weird. I'm honestly start thinking that this is just a good challenge. What? Wait, let's open the resource hacker again. No, wrong program. No. Resource hacker. Yeah. Let's leave the cursor sound. Yeah. Never gonna give you up, never gonna let. Whoa. Wait, what? The fuck is this? Let me see something pretty quick. So for example, let's take, I have a WAV file here. I want to understand the format of a WAV file. Is this normal? Lol. This is not normal. If you see, can you see the difference? The seat is broken. Info is FT. Oh my god. Okay, what's that? Oh, metadata. Let's run exif tool on this file. But you can see that this is not normal at all. This is not normal. Anyway, you know what? Let's look for these bytes. Let's look for these bytes pretty quick. We can look at here. No, actually, in the entire memory. And look at for these bytes. But this is assembly. Ah, no. Never mind. Okay, so let's, for example, put a breakpoint. It looks like it's short. We must short everything with 80, with value 80. So for example, let's put a breakpoint here and run this. What? How is it possible? Oh my god. Oh,
But with the PC involves in the data subchunk. Oh, okay. So we care about this data string that we find everywhere. Let's actually jump to this method. Let's jump here. So what is EDI? Struct init SAS numbers. Okay, let's modify the output of this with that and let it run. What the fuck? What the hell? What is being hashed? So this is the hash. Okay, and this is my input currently. I2 v31. So RDX. What's the value of RDX? Oh, what? This is hash. Where are these? Oh, where are these bytes? Are they inside the WAV file? No. You can see that they are always changing. They look pretty random. Um, yeah, let's put a breakpoint here. What's that? Start address? Oh, this is very sus too. Yeah. Okay, so we've got a message box. What? Should we? Is this? Wait, is this a binary? An MZ file? Okay, let's take this and move to CyberShell. Yeah, but this is guessy, I think. I'm not sure this is right. This is really guessy. From hex dump. No. Then paste it. Crushed. Come on. Thank you very much. Okay, these are the low bytes. Okay, so let's XOR with 80. Does not look right to me. Yeah, it's not it. There must be something else. Oh, so let me check something again. So I have, do we have breakpoints? Okay, this is the hash function. Yeah, this is the hash function. So let's run this shit and click play. No, we don't want any hardware breakpoints. Let's run this and we get that. Okay, so let's take this value and run this. Now remove the breakpoint. What the heck? Wave out right. Okay, let's take a look at these methods. Wave out right. The wave sends a data block to the given waveform output device. Okay. It's good. Let's move. So it will jump here. Okay, we want to jump here. Very weird. Wave file executable P. Oh, steganography P loader. Oh. Oh shit. Oh shit. The header of a WAV file is 44 bytes long and the last 4 bytes indicate the size of the data section. Show.wav, the data size. Okay, in the code snippet below, the loader reads these 4 bytes and uses the value to allocate space in memory. Oh. We're going to look. Okay, this is very interesting. So tells us that we skip 2 lines and last 1A. This looks legit. Oh my god, seems that
Dude.
what? It's the first time I'm seeing something like that. Wave out. Okay, let's open this. Let's put a breakpoint here. Wave out, prepare header. Let's prepare. Let's put a breakpoint here. Run it again. Play. Okay. It's loading the same address. Let's put a breakpoint here. So it's the EDI that we want. So what's this target value? Where is this coming from? 336. Let's look for this offset. Sequence of bytes. So 7. Okay. Oh, there is it. There it is. There it is. The target hash. So the target hash is initialized here. Okay, I know what we have to do. Okay, I think let's put a breakpoint at this place. So let's go here and put a breakpoint and run it again. Yeah. Fucking. Yeah. So let's run this. Okay. Okay, let's dump this. Okay, we want to put a breakpoint here is the word. Now it's old. Where it is here? One breakpoint here. One here. And one here. Let's run this. And the code breakpoints inside memmove. Okay, we don't care about that. Let's return. Let's run again, and the code breaks here. Very interesting. So let's run exif tool with the sound, but I doubt that this is something. Yeah, of course, it's not stego. Yeah, this is fucking cell code. I'm pretty sure. So thing is, how is the shellcode loaded? Is there a virtual alloc call? No. Is this called anywhere? Okay, let's put a breakpoint here just in case, but I don't think so. Okay, now let's run. And we hit a breakpoint at this line. Let's move here. What's wrong? Oh, it's false positives, of course. Oh, excuse me. I think struct init. So, no, wrong breakpoint, wrong. That was wrong. We need to put a breakpoint. Yeah, let's remove this. Yeah, I'm pretty sure it's shellcode, but need to find where. Okay, let's put a breakpoint here. Let's run again. Don't mind. Okay. So, what's this? So what the fuck is going on? So RAX. Oh, it's RDX. Yeah. So we need V5. So that would be RCX. So we need to go to RCX and put a breakpoint here and move on. Oh, we hit a breakpoint. Where is it? Okay, this function is more interesting than we think. It's chaotic. Oh my god. This does some crazy shit. V20. This is a decryption loop. Oh, this is a decryption loop. suspicious. It looks like it does some wave function decoding thing. So yeah, so this is where did this come from? Okay, RAX plus RDX. RAX, what the fuck is this? Oh, 9091. Let's run for search for this inside here. No, I think it's not right. 9797, 9899. This definitely looks like XOR to me, seriously. So let's look for this. Oh, this is very common. So is this present anywhere? It's not present. Oh my god, this is so much XOR. I know it. I know it's XOR. Okay, R12 is then it's R8. Okay, R8. What is R8? Oh, oh. Let's see. So, oh, so this is a XOR constant. Okay. So where is this exactly? This is fucking ugly. So V25, what is it used for? Do we need to set this to the target thing? Yeah, I think this is it. Maybe we need to override this one. Okay, let me check. So let's put a breakpoint also here. Yeah, and here. Let's run this exception. Okay, assume that. This is literally a decryption loop, but R12. So what's the value of RSI? Oh, this is where it's written. RSI is 1. So RAX. I see. And we're debugging until what? Maybe we see something. Okay, so this is the where the data are written. For example, I'm pretty sure that the wrong value is used for the XOR, so we need to figure out the correct value. Let's run this quite a lot, a couple of times more. I think now this entire value will be hashed and verified along this target hash. So I'm pretty sure that the wrong values. So if you see our rate is never changing, right? So it's always the first hash that is used. Maybe this is wrong. We need to change to the second one. We'll take a look. R9 racks RSI. So it's RSI and RBP, now they're equal. Okay. I see. So these are the 15 bytes. Let's put another breakpoint here so we don't miss these values. Okay. Compare RBP with F. Of course it's F. What's the RCX? Okay, RCX. What's the RCX? Hardware breakpoint. Oh, okay. The byte is called. And now what? And now what? Now what? RX. So it works. Okay. Let's put a breakpoint here. What? This is so fucked up. Oh. Uh-huh. Ah. Okay, is this shellcode? Of course not. Of course not. This is not shellcode. Yeah, so I think we need, anyway, let's go. Move on. Oh my god. Let's write the data. Okay, the algorithm is pretty complex. It's doable to re-implement locally, but pretty complex. Okay, 2 more iterations. Let's go. 2 more. Okay. So these are the bytes that are going to be fed inside the method. So now the hash is computed, so the target this is the, I don't know what the fuck is this, but RDX should be the row buffer, yeah, and R8 should store the number of bytes to be hashed. So this is 0x17, which is 23 bytes. So 23 bytes are hashed and compared against the target hash. I see. So I assume that we have to find the correct key. Yeah, because now if I patch this value, for example, if I take this value and I move it like that, then it will work. And we will get prepare for the rape. I think the intended thing to do is to override, to try any of these values until we hit a match. So let's move on and set a breakpoint here. Okay. Apparently this byte. Okay. Let's go here and following dump. No. F9. Okay. Now we need to jump here and override with F6 B606 3B. Yeah. What? FC. Yeah, I don't know. 6B6063B. Okay, this is the path value. FCB6063B. Let's run this. Gosh. 17, of course, and even to the end. Of course, it's not the right thing, but if we I think so. Okay, then what? This is the wrong hash again. The wrong key. Okay, then let's move on and try. No, give me a moment. Let's move on. I think this is the intended thing to do. But of course, I'm not sure. Like, if we actually wait, where is 50? Oh, plus 23. Wait, this is 4, 8. This is 32 by 4 multiplied by 5, 4 by 20. What, are you serious? So these are 23 bytes actually. V2 plus 39. It's pretty obvious. Like, this thing is wrong. How am I going to know the correct one? Oh. Where is no. Why doesn't the recall play? If I run this, never gonna give you up, never gonna let you down, never gonna run around and desert you, never gonna make you cry. This is painful. Painful. So painful. Let's move to SAS. Very SAS. Let's move to this part. And let's put a breakpoint here. Okay. So, what's RAX? Where did this value come from? Where did this value come from? No idea. My assumption is that no assumption actually. 99 okay. So this is the keys. You can see that they are 23 bytes. So 20, 21, 22, 23 bytes. So I assume that, so let me grab it. So this is the key. Okay, this is the key. Let me take the plain text, the presumable plain text. I don't know what this is. For example, this. And sure. Oh my god. So this is A1, BA, A9, etc, etc, etc. Okay. So this is A1, nice. BA, A9, 6A, 6, 9, yeah, 9E, right? So C5, 8A, that's all. Then oh, R9 is accessed. So we have more encrypted data. It's not okay. What's more? So R89 is 0B. Key 16 is 11. Okay. And it XORs it with R12. which is 95. What's the length of this? 15. Where is what? Wait, let's move back to RDX is 1. What's RAX? Oh. Oh, okay. So it's all about, okay, I see. This is ridiculous. Ah. At least I know what's going on now. Okay, this operation is not that simple apparently. So it's plus 280. We need to look for these offsets. So it's 280. 280, 288, 296. They're all empty. Okay, let's start with where is SAS2? So let's take a look at this offset. Okay, let's search for this offset. How is it possible? Never mind. Okay, let's move on with this one. Maybe it's static. I don't know. Nice. And this one. Okay. Okay. So regarding this is a move RDX. Okay, this. So, oh, this is so ugly. This is so ugly code. Wait, does this do? This is pretty sus as well, but I've really not digged in that much. Yeah. Anyway, am I supposed to guess the encryption key? Switch 1A. Let me see. So apparently this entire thing is short, it's corrupted, but for some reason when you execute it, it works. It plays Rickroll. What? WAV file, malware, sure. No. No. That post we found before was excellent. It really was what we wanted. You can see the data. Oh, okay. So it's a 4-byte value. Oh. Oh, what? It's read in reverse? What? So is it 96, 98, 98, 95? I see. Is there any reference to the data string? No, I mean data. Literally. No. Data hex. So we need to look for sequence of bytes 61, 60 in reverse. Nothing. Do we need with the reverse NDNS? 64. yeah, this looks like a parser, wave file parser. It looks like it parses the wave file. And then stores some shit here. This looks interesting. So v6 is the data. This is the offset. Okay. So this should be the encrypted data. Let's put a breakpoint here. Write WAV data. Let's run again. Exif tool is garbage. Okay, so this function is called only when we load the yeah. So this is WM, no, what's that? Let me tell you. Yeah, I think this has to do with the buttons. So okay, I understand. This isn't okay. Button dispatcher, I understand now. This is what runs when we click play, this is what runs when we click about, and this is what runs when we click exit. So on click play, on click about, on click exit. Oh my god, this took me so long time to figure out why. Anyway, so okay, this is very good because we know now that we can isolate our research on these functions only. And more specifically, this is trash function, so if probably these functions. This is some short thing as well. Okay, and this this actually play WAV. This actually plays the WAV file. It opens it, etc, etc, does some shit. Yeah, of course it's more complex than that. What? Okay, bro. Let me change something. Okay, let me change this. This is the final thing. Okay, I'm not going to bother anymore. Okay, play. Fuck this. Okay, so we're here. We want what's the data in here. Okay, we want so not that one. This is very sus 2. We want B0. So you can see that this is empty. plays in reverse. Okay, let's open this up in Audacity. I'm pretty sure wow. It plays normally, like nothing's wrong. Wow. Okay. So what does this function do? Performs a waveform, prepares for playback. Okay, so this is decrypt wave file, if we can say. Yeah, so this decrypts the wave file, and the wave outright actually plays the file, if I understand correctly. So if we put a breakpoint here and let it run, fuck this. What? Wow. Data block. Prepares. Okay. And pointer to the data block. Okay, so we need RDX to find the actual data block being written, and the header looks like, okay, it's pretty simple. The raw data is here. This is the block. Is this it? A1 BA. No, it's not. Okay. Let's run it again. Sorry. Let's play and click on RDX on here. Okay, so this is the data to be played, to be playbacked. Let's see again. This is the method. Yeah, this is the data. Okay, so what is the size? NP data buffer length. So what's the second? It's 20. Wow, it's 8,192 bytes. What is the data block size of wave file? Okay, I'm pretty sure that okay, now I am starting to understand what's going on. It literally, there is a wave file, and it literally has created a whole parser for it. It parses the header, and it literally plays the sound block by block. So we need to, and apparently, okay, that would make sense. Apparently, when where is it? There should be one block that for which the hash match. Then, oh, this is called. Oh yeah. So what's SRC? SRC, don't know. Oh, this is the block. Okay, V33. Okay, we need to find this offset. So what the move RCX in the end? It's null. Let's put a breakpoint here and see the value. This should be the encrypted flag. Or what? Uh-huh. Oh yeah. What is it? Yeah. This is a function pointer. Okay. Oh, okay, okay, nice. So which function is called? Okay, okay. This is interesting. So 7, 7. The second function is called. This is a 0, 8, 16. Let's move. Okay, so this function is called post message, of course. This looks like it decrypts the flag. Is the block length, the block data size wrong? Oh, interesting. So let's move ahead. So wave outright. It's 108,000 bytes. Okay. Okay, this should be part of the WAV file. No, no, sorry, it's control F. No. '92, '95, '97, '99. Yeah. What? Let me check again at the actual WAV. Damn, this sucks. This sucks so much. Come on. My mouse is... I'm just ranting over my fucking equipment that is bad as hell. I want to see the last data block, honestly. Just the last one. In case there is any pattern, but I'm not sure. Oh wait. Oh wait. I know what's wrong. Oh fuck. Oh shit. I completely know what's wrong. Getting annoying. Ah. This is a data block. The last data block though. Of course it's not. This looks like the end. Okay. Look. This is the Rickroll thing, okay? So, look what happens. Oh shit. Okay. Before actually writing to the file, there is an additional XOR with a constant that we need to eliminate. Check this out. So the actual data that are written is 91, 91, 94, 96, 97, 97. But here it is 91, 91, 95, 97, 97, 97. So it's this is basically XOR with the value the bytes 1100. So if we repeat this process here, it's the same. If we XOR this with 1, we get 99, which is the actual ciphertext. And no, if we XOR this 99 with 1, we get the target one. So somewhere the data are XORed with the value 1, which is something we don't want. We need to eliminate this XOR thing. And I think I remember this function that was responsible for the XOR. It was a short one, a really short one. Wait, I'm gonna find it. Wait. It's wait. It was this. Yeah, that was it. I think. No, maybe not. In any case, we know now. We know what's wrong. This is a good thing. Yeah, I think that's it. Yeah. Okay. So take a look at this now. For example, this is the second block of sound. No, this is the first block. If we XOR everything with 1, we get this. So do we need to XOR everything with 1 here? Oh, don't think so. I think the intended thing is that the thing is that this file is correct, so we need this file to play actually. Okay, I see. Okay. Let's run again. Okay, this is wave file read. Yes, read wave file. What was my naming? No, it's not real parser. Is it a parser? No, we read wave file. It's your reader. Okay, let's call this and move on to the bottom and see the actual data being written. So this is AF. Okay, let's follow this in dump. Okay, this is actually, oh, this is 0A. Okay, so it takes this value, this is the value of the data, and apparently this is the address, data start. Can we make sure this to get the key? Nah, I don't think so. Anyway, this is the D word and and it reads that many. Oh, so this is the length. This is the length. Okay, this is the length of the data. Something like that was this one. So it's 720 kilobytes. Okay, and V17 is what matters, and it writes it to the beginning. Okay. No, how is memcopy? Oh, it's the source is here. So what's the source? Okay, let's move down to RDX. Okay, this is the start, and it copies that many bytes. What? Let's move to RCX and see what data are written inside. Here it is. So what's that? Plus this value. Yeah, this is it. So we need to jump to this address precisely. This is exactly the end of the file, and I assume, yeah, okay. So let's search for this thing. This should be the end of the file. Yeah, I see. Okay, okay, okay. This is clear. Okay, I think I overcomplicated this challenge much more than needed. So this is let's move to this function. What's that? I don't know. Let's see. Huh? Oh, this is SAS. We actually need to convert this to zeros. No sound. Okay, that works. Yeah, these are the raw data. Oh, it reads them in reverse? Wait, do we actually have to start from the first block, but we start from the last block? I'm not sure. I'm not sure. I'm not sure that that's the case. It could be, but I'm not sure. Okay. Let's skip this function. It looks trash. What about this? Also looks trash. This looks like some dumb shit. So 20F0, this is it. Yeah. So now it's time to go search the memory for this pattern. Of course, it's here, not the resources. These are the resources, these are the loaded ones. We need the loaded ones. So let's go ahead and put a hardware breakpoint here and run this. Oh yeah. Where is this function? Oh. Oh shit. I was afraid of that. So this is the function that does the problem. Yeah. So it's E48 RBX. So where is it? It's E48. Yeah, it's this line. Plus R8. R11, R10. So it does something to the entire, oh my god. Look at that. Yeah, RBX 91. Okay, what's the actual result, please? Some shit. Yeah, what about it? Yeah, so far the the data are not corrupted. I think we could just skip the call of this function. Yeah. Okay, let's move on. Where is this called? It's called here, and it runs until what? Oh, this runs per block. Ooh. 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 Oh, this shit. I think this is the problem over here. Okay, did we put a breakpoint? Yeah, let's run this. So this is 8F. I see. 91, 91, 94, 96. Do we have this pattern? Whoops. Leaks. 91, 91. Here. Oh. I feel that I'm close. I'm really close. There's something going on here, honestly. You know what? I seriously don't understand. So, okay, so we need V20. Is that V12? 312, yeah. We actually need this address. Let's put a breakpoint here. Hmm. What? Oh, this is the key. Short key. Hmm. So this is a short key and it's a car pointer. Yeah. So there is a problem. This big thing. Oh my god, this is ugly. So the XOR is intended to work as it is, but yeah. So this is N35 block. So this is a source. Okay. This is the beginning of the this is the end of the key. So this basically says while the key is not finished. So if it's finished, so yeah, this checks if the block is processed. Processed enc block. While the block is not processed yet, counter μικρότερο του 23. Yeah, so yeah, this is the ciphertext. Yeah, this, I think this is a counter. Yeah, this is a counter, so we can replace it with J, and this can be a car pointer. Perfect. Encrypted, so this is encrypted car. The encryption part should be left as is. We are aiming at encrypting this, but for example, let's move to this part. So wait a minute, let's move to this part. Yeah, okay, let's move here. We want, look at this, we want, you see that this is the modified block. We don't want this. So let's go ahead and replace this with this one. So let's have it side by side, and let's go ahead and process 23, no, 20 bytes, 16 bytes. Yeah, 16 bytes. Yeah, so this is 99, is correct. So 95, 97, 97, 97, 97, 99, wait, 97, 97, 99, no, 97, 97, 99, 98, 9A, sorry, 9, 9A, 99, 97, 95, 92. Okay, this is correct. Ah, this is not processed yet. Yeah, of course. Yeah, this is not processed yet. Of course. Wait. Let's do it. So 91, 91. 95, 97, 97, 97, 99, 9A, 99. So yeah, we patch this. The right breakpoint is here. So 92, 95, 97, 97, 99, 9A, 99. So we finish with this block. 99, 90. Let's have it side by side. So check these values of R12. 99. This should be 97. You see? I don't understand the encryption logic though. How is the bytes modified? I don't understand this. Anyway. Okay. So this is 95. Oh, now I'm confused. Wait. So it's 95, 90. No, this is wrong. Let's go ahead and run again. Yeah, I know. Okay, so RAX. Okay, let's replace the entire thing. Ninety-five, 97, 99, 9A, 99, 97, 95, 92, etc, etc. 8F, 8D, 8D. Wait, this one should be 91. Mm-hmm. 91, and now next 7, 20. Yeah, I will need to replace this as well. So that would be 96, 99, 98, 96, 95, 96, 97. So I think that and so on and so forth. So I think that the entire thing is short with a standard 0 and 1 sequence. If I literally copy paste this and move it to a WAV file outside, if I play the WAV file, so if I copy this corrupted wave file here from the debugger, from the inside the program, and dump it outside, if I just double click, I'm not going to hear the rickroll as now, but I'm going to hear this reverse thing, the corrupted one. Okay, so I think we figured out what's wrong. Now we need to understand where the actual code is patched, so we can figure this out, remove the patch entirely. So this is I 296 Oh, you see that? I think this is it. Ah. No, maybe not. Oh, I need to remove one. Ah. Does this actually corrupt it? Wait, 91. Oh, wait, V18. V8? What's V8? Oh, this is V8 is A1 272 plus 8 plus 8. This is 280. So this makes a new block, and yeah, I think this is where the actual byte is patched. Let me check this out pretty quick. Here is where bytes are patched. Let's make this sure. Play. Oh, yeah, exactly. This is where exactly it gets patched. Precisely. You see that? Look at these bytes here. 96, 97, 97, 98, 99. While it is 97, 97, 99, 9A. You see that? So V9 is the corrupted value, and it's calculated somehow here. Yeah, so this is corrupt corrupt wave file. Wait, no. This is yeah, we basically have to how can I say, compute corrupted byte, something like that. I feel that we're close. We're very close to the solution. So this is the corrupted byte. Otherwise it's dereferencing. Otherwise, so patch the byte, not corrupted, because it depends on this value. So it depends on this value. We can either patch this value so it always evaluates to false. If it evaluates to false, then we always get the real value, the real value from the file. So this basically reads the raw value from the file. In case it's true, this is true, it computes the corrupted byte. So we need to figure out basically how is this value computed. We need to figure this out. I don't know how. yeah, yeah, this is where the magic happens. Let's run this again and click play, and you can see that, for example, wait, this is 1. So why it does not compute the corrupted byte? Compute patched byte, patched, it's patched. Okay, so wait a minute, it actually, oh, it's 91. Never mind. Okay, yep. Here is where the magic happens. So if we put a breakpoint here, it will never trigger, presumably. Exactly. This is the entire problem. So we have to set this to false. Yep. But if we run this and sorry, we want to yeah, this is verified. So we need to move to where? Not here. We need to move here and modify this. Bam. Boom. Okay, we need to modify this to 75. How can we patch? Can we patch like that? Yeah, okay. So jump not 0. So now it always jumps here. We can keep this value as is, unpatched. So we can either patch this from jump equal to jump not equal, so it always jumps here and keeps the original byte. Keep the original byte from WAV file, patch the byte. Okay, I'm not sure. Anyway, so our choice was to patch the if statement. Why? Okay, patch this to jump not 0. Fix 1 actually. Patch this to jump on 0. So this is the first fix. Now I assume that we need to run to find why the data are read in reverse. Okay, let's read the description again. So one controls the direction the record spins, the other spins keeps the pitch steady. Controls the direction. So we patched, I think we patched this one, and we still have to figure out the direction, and then the challenge is solved. Okay, this is very interesting, very nice challenge. Wow, I am shocked. This is very good. Wow. Now that I think about it, wait, can't we just solve it statically? Like grab these values, like grab all of this, and take the XOR key. Yeah, it makes sense. From hex. No, let's remove the everything from here, and XOR with what? With struct. So this is it's moved in another window. This is 32B3D FC F6 P6 06 3B 0E B1 ED C0 E1 48 07 0C 0B BB F4 F9 48 01 19. Will this work? And crashed. Oh, it did not. Oops. Yeah, I think this is not correct. Yeah, I'm not sure what exactly should be short. Never gonna give you up, never gonna get you down. Na, 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 na. Let you. Oh, you know what? Let's do something for fun. Patch file. Fix steady pitch. Okay, now we can remove this name this to original and rename this to .exe, so we keep the labels. This is temporary fix. We're going to make sure afterwards that it works. So yeah, can we reverse this? Yeah, I think this will work. Pretty sure. Oh, seriously? How? How is it possible? How is it possible? Okay, then we need to figure out why this happens. I think this is gonna be more tough. So now if we run this, we can hear the sound, but it plays in reverse. So so we don't have to bother with this anymore. Apparently the data that gets here are already in the wrong order, right? What does the description say? One controls the direction the record spins, the other keeps the speed steady. One controls direction. Oh, I see. So most probably we need to... Is this it? Yeah, this looks like it. No. At this point we are already at the last block. What's V14? It's a length? Let's take a look here. Oh, yeah. Now I'm curious. Would it be possible if we found a way to trace which if statements are never reached? So, that I don't think that's possible anyway. Okay, let's rebase this again because we imported the binary. What? Process stopped. Oh, okay. Then let's copy paste this, edit segments, rebase. No, it's wrong. Address. Okay. Then we need to get where? No, wait. Yeah, I want to get here. 10. Okay, let's get here. So let's play and compares. So it gets here. I don't think so. Nah, that doesn't look right. Nah. No. Definitely not. Question is the direct in reverse. I think what we're looking for is outside of this function. This shit is fine, pretty sure. Yeah. Question is, should it read it like so this is 16 bytes. Wait, this is 16, 17, 20, 19, 20, 21, 22, 23. So should it read it like from here to here, or the opposite way? Okay, we need to put a breakpoint here and see if this is the right place. Let's run again, play and check. Oh, I think this is a problem. Where is this value? Let's see what's wrong. So this reads the second from it skips the last byte. Yeah, so this should be data PTR. There's something going on here. I think this is the problem. Where is this value written? We should look at this value. This is where the problem begins. So play wave file A1 16 before. Oh shit, here we go. Oh yeah. Let's run again. Play. Oh yeah. I see. So yeah, we need to get here. Exactly. So this is V16 2196. Can we just make it 1? I'm getting tired, but I need to solve this. This is over. I need to solve this. $24. This looks like something that might impact the result later. Oh. Oh, okay. I see. Maybe this is the order. Okay, so we need to breakpoint here and check the value. So let's run again. Oh, this is the reverse direction. We might need to patch this to 1. Right?
Never gonna give you up, never gonna let you down, never gonna run around and desert you, never gonna make you cry, never gonna say goodbye, never gonna tell a lie and hurt you, never gonna give you.
And we got the flag. This is it. Fuck yeah. That was it. So this offset, this plus 24 thing is the direction that the record spins. So -1 means that it runs on reverse. So we need to switch to 1, and then since it's a 1, the value before is 0, so it starts from the beginning and increments by 1 each time. So the blocks are processed sequentially. Now my question is, we're not done yet. Even if I patch this, okay, suppose I patch this. Let's stores the record, the direction that the record spins. Normal. So we have to either patch this to jump 0 or change this value to 1. Right? No. Yeah. Compare. Yeah, we need to patch the jump. Okay. Okay, so let's go ahead and run this again one more time. I want to check something. So yeah, we run it, play. Okay. Wait, I want to get in here afterwards. Here. Okay, so I want to patch this value to 1. Okay, and then this is the pointer. Oh yeah, it starts from the beginning. I see. So this is crystal clear now. So yeah, this is it. Now my other question is, what happens when we get to this if statement? Like, okay, the hash matches and we get here, but there's no code, so we need to call breakpoint this, and
Never gonna give you up, never gonna let
need to wait. Okay, so it found the flag. Wait, what? Where is the flag? Wait. So there is some block containing the flag, not reverse. Keep it as is. CMO. Am I missing something? So this should be the entire thing, right? Short with this. What? What? Okay, so the flag appears here, but what the fuck is this? This does not look okay, so RSP plus 50. What is it? So is this it? No, wait. 26AE. This is it. Oh, so the flag is 23 bytes. Oh, okay. So the flag. Okay, so wow. One of these encrypted blocks is the flag, apparently. Thing is, where is it? There's no flag here. Have I fucked something up? I guess it's not just short. So let me get in here. Let me put a breakpoint here. Okay. So let's patch this out to just 1, or just change the jump not equal to jump equal. Let's run this, and so RAX is the 8 byte. Okay. What about R8? This looks legit. This is legit.
Never gonna give you up, never gonna let.
I guess the encryption slash decryption is not just XOR. There are more operations going on. Oh, the XOR key is updated. No, this is the offset. Yeah, so this is it treats it as 23 bytes. Yeah, I see. Now I'm curious. We can make this, no. Okay. Okay. So R9. Yeah, this is the key. It's clear. Crystal clear. Yeah, I see. Let me check something. Maybe I did something wrong. What's sol.py? Yeah. So let me yeah, let's open the WAV, read bytes, and read the enc. So enc, no, raw data, file data, the raw data are file data from what offset? What's offset? The offset is 50. Oh no, it's not 50. Oh no, it is. Is it? Yep. So no, wait. Yeah, exactly. So it's 4e. It's 4e until -1, from pawn for XOR and print XOR raw data with XOR key bytes from X. So the XOR key is R8. This is XOR key. Copy data string. No, it's C style hex. No, C style. No, hex string. Okay, let's check. UV run with pawn tools. Six hours long. Okay, in general, I think I overcomplicated this challenge. It could be probably easier, I don't know. But I now understand exactly how it works. It's detailed. So this is let's check if the flag is in the tech data. I don't think so. Ugh, sucks. Okay, let's print the first 23 minus the first 23 bytes. So that would be that. Okay, so let's so what's that? Okay, let's move on. Okay, never mind. Let's change this to jump 0. Okay, and RDX. This is totally wrong. What the hell? What? Yeah, let's run this again. I'm not sure. I thought it should read 80, just 80, 80, 80. No. By the way, this is where's the crypt play. Pass this to jump 0. Yeah, okay. So let's move on. Okay, so array, no, just breakpoint here. It's enough. So R12 88. Oh, what? So what? It accesses 80 and 9091. What? Is this anywhere? No. Okay. 97, 95, 91, 91, 80. No. Fuck. Wow. So is this seriously? You're fucking kidding me, right? Are you fucking kidding me? So this should be first byte plus everything from there minus 1 and reverse it. So is this it? I think this. Oh my god. No? I think I know what's wrong. It does not work as I expect it to work. So I think it does something like it takes this block and combines it with this 80, then takes the second 80 value f80 and moves on to the second block, and so on and so forth. The second block. Yikes. Okay, let's see what about the second block. 46. Is that it? Yeah. So let's rerun. Yep. And patch this out. My head is hurting right now, seriously. And yeah, this is it. And where is the no, here. So this is the first block. Okay, so let's move to the next block. What's the second? We confirmed that this works. So what about the second block? Now let's wait, what? The same thing again? Yeah. Anyway, this is the decryption thing. This is cursed. I'm not going to reproduce this, but you understand the logic. I assume that, okay, let's run this quite a few times. Okay, now of course the hash will be wrong. Oh no? No, yeah, it is. So it's definitely wrong. Yeah. Yeah. So what about RAX now? I don't understand, seriously. The first block. So this thing is parsed so many times. It's like the first block is decrypted with its possible key until the hash matches. What? I don't understand. Let's break point here actually. Okay, so RCX multiplied with 8. So this is it. What the actual fuck? While 1. Yeah, this repeats on and on. Oh wait, oh. This is there are 2 loops. This is the first loop and there is an outer loop as well. Oh shit. Yeah, this is painful. Anyway, I'm not gonna bother with this one now. There is some reason that it's an easy. You're not supposed to do all of this work. You just have to patch out the right things. Of course, it would be a very good exercise to do this statically, 100% statically, but it's very painful. I think it's very painful. Yeah. This is basically very painful. Yeah. Simple as that. You know what? We could actually... Nah, it won't work. Never mind. Okay, this is the challenge, guys. Here is a flag. So I'm not sure I'm playing the rest CTF. If I decide to play, it will be after I will be after solving it, so not during the CTF. And I also owe the two last Flare-on challenges from 2025. So yeah, that's it from me, and see you on the next one. Bye. Hope you enjoyed it.